Hello everybody, my name is Bill Cope and this is Mary Kalantzis. We're very pleased to be with you. It's this strange virtual be with you. It would have been nice to be able to come to Germany, but of course we're not there for the reasons of this pandemic. And one of the great ironies is the topics that we're talking about in this conference are all of a sudden even more important because almost all our human interactions are now mediated by these digital media. So thinking through what they mean and how they work and what they do has become even more important than ever.
Yes, hello, I'm Mary Kalantzis. Bill and I both work at the University of Illinois, but we are talking to you today from our home in Urbana-Champaign because we, like many others here, have been, I think, in lockdown now for almost 3 months. Engaging like this has become the norm for us, and I want to thank the organisers of the conference for including us in today's discussions of what has become even more critical now than ever before.
Okay, so as we now launch into the formal part of our presentation, I am going to share a PowerPoint presentation with everybody. So, and Mary's going to kick off. So over to her to get started on that presentation.
Right. Thanks, Bill. So, artificial intelligence. It's in the news. It's everywhere around us. People talk about it all the time in one way or the other. We have techno enthusiasts who think it's kind of the most important thing that's happening in our world. And then we have techno paranoids who are anxious about what artificial intelligence might mean for the nature of life and our relationships. However, neither of them are terribly clear about what it means. I mean, the term is used very loosely most of the time, but the truth is that it's around us all the time. It's in our media, it's in our Facebook, it's in our social platforms, it's in our regular newspapers, it's on our bodies when we have devices that count our heartbeat, etc. You know, artificial intelligence in these places is gathering data seamlessly and endlessly. And it's getting to know us in order to deliver to us targeted advertising or targeted medicine or targeted learning. It's a huge evolving field. So how do we theorize it? How do we conceptualize artificial intelligence? Well, we're going to give you two ways of thinking about it. First, AI as the mechanics of media, the theory related to that. And then the second part is learning with AI, where we claim the medium is the message. So what does artificial intelligence look like in practice? So, computability. How do we understand computability? Because of course, artificial intelligence is encompassed in that notion. And what we're going to introduce to you today is an idea that we've been working on for many years now, but to say that the transposability of meanings into calculable quantity is what computers can do for us, right? And we have two broad meanings in the definition of AI, right? So the broad meaning is that artificial intelligence means that meanings can be made with more calculation than would be feasible without mechanical intelligence. It's a very broad understanding. The narrow understanding of artificial intelligence is that it is the synergistic human-machine relations of machine learning specifically. So, a little history. Here we have Gottfried Leibniz, the great 17th to 18th century philosopher and mathematician. Now, Leibniz had a fantasy, and his fantasy was to imagine what all meanings in the world would be like if they were expressed in numbers, if every truth in the world could be determined mathematically. And famously, he said, where there are disputes among persons, we can simply say, let's calculate without further ado, in order to see who's right. That's how far he thought he could take calculability. Moving forward now to the 19th century, we meet another mathematical genius, Ada Lovelace. She had inherited her love for mathematics from her mother, Anna Isabel Noel Byron, the 11th Baroness of Wentworth. Anna's husband and Ada's father were the poet Lord Byron. Ada's father dismissively called his wife the Princess of Parallelograms. Dismissiveness like this was the fate of women thinkers for far too long. However, by the age of 18, Ada Lovelace was introduced to the inventor, Babbage, at one of the high society soirees he regularly held in his home in London. She was attending with her mother, and on display in the drawing room of Babbage's house was his difference engine, an elaborate mechanical calculator, which you can see here on the right. Ada was transfixed. This began a long professional association between Babbage and Lovelace. Their work together culminated in 1843 with the publication by Lovelace of a 20,000-word journal article about Babbage's design for the new analytical engine. Lovelace simply signed the article with her initials ALL in those days. Who could have imagined that this was written by a woman? And here are some of the words of Lovelace's article. And I'm sure you'll agree, for someone writing in 1843, her remarks are remarkably prescient. By mathematical representation and calculation, she said, it may be possible, again to quote Lovelace, to express the great facts of the natural world and those unceasing changes of mutual relationships which, visibly or invisibly, consciously or unconsciously, to our immediate physical perceptions, are interminably going on in the agencies of the creation we live amidst. Lovelace continues, the analytical engine weaves algebraic patterns just as the jacquard loom weaves flowers and leaves. In these ways, not only the mental and the material, but the theoretical and the practical in the mathematical world are brought more into intimate and effective connection with each other. The model for such mechanical possibilities, Lovelace went on, was the principle which Jacquard devised for regulating, by means of punched cards, the most complicated patterns in fabrication of brocaded stuffs. Lovelace, I think you'd agree, was truly a modern genius, imagining how the qualities of sensuous world might be transposed into quantities for the purposes of their representation and communication. Ada Lovelace had imagined how, in the future in which you and I now live, we might be able to build machines which manage the transpositions of quality into quantity. Over 100 years later, one of the main founders of modern computing, Alan Turing, turned to Lovelace's largely forgotten article and was able to build upon some of her key propositions. After the Second World War, Turing worked at the University of Manchester in one of the world's first computers. One of the first things Turing and his co-workers did was to use the computer to find some huge prime numbers which it wasn't practical for humans to find via hand calculation. Here we see a printout of the computer, and here is Turing getting a surprise. How did this happen is his note on the teletype printout, as you can see circled in red. How did the computer arrive at this calculation, he asks. Perhaps it was a bug, or perhaps it was a new insight based on so many laborious calculations that no human could feasibly achieve. So for him, machine intelligence is much less than human intelligence. Computers can only calculate, but it's also much more. Computers can calculate more numbers and faster than humans. We have cause to be in awe at the superhuman brilliance of their feats of calculation, but we also need to be cautious about what computers cannot do. So, to conclude, Turing called this mechanical intelligence, and hence we have a broad definition of artificial intelligence, which says that what it is meanings that are made of more calculation than would be feasible without mechanical intelligence. However, in the narrow definition, the notion of machine learning is central. Machine learning means that humans are training. I'm sorry, I moved that. Oops. Oh, I'm sorry. Okay, back to the slide. In the narrow definition, however, machine learning is central to the understanding of artificial intelligence. Machine learning means that humans are training the machine to notice things. These human trainers might be experts, or they might be massive users interacting with computers. And fundamentally, there are two kinds of machine learning. Supervised machine learning is where humans label things for the machine to count. So just to give a simple example, when you like something on Facebook, or when you give a high ratings for something in a product review on Amazon, you are teaching that system to know about you and people like you. These are simple examples, of course, of how environments become smarter the more people use them. Now, unsupervised machine learning is when the machine makes calculations that reveal statistical patterns. For example, a cluster of things appearing, or alternatively, it identifies one or a few outliers. Machine learning always involves the synergistic human relationship, whether it's in one direction or the other, supervised or unsupervised. So with supervised machine learning, the direction is the humans label and the machine counts these labels. With unsupervised machine learning, the machine counts and the humans label. The important point here is that this is always a synergistic relationship, and no matter how sophisticated the algorithm seems to be, they are relatively crude and simple in relationship to the meanings that humans ascribe by their labeling.
So the question is, how does calculation happen, and how far can we go with calculation? And what I'm going to argue is that the limits of artificial intelligence are the limits of the transposability of meanings into quantity. And by transposition, I want to talk about 4 possible processes. The first process we call namability. So what we have on the left here is names of things in the world. So here's a bag coming off the conveyor belt in an airport, and it's been given a name, which is the long number, which is written in the barcode. And this, if you like, is a kind of proper noun. So here's Mary, she's a proper noun. This is something which is specifically named as an instance. On the right, what we see is something that we would call a concept. So if Mary becomes a concept, she's a person. Here we have a product. There are many, many of these sardine cans. I might take 3 or 4 of them to the checkout, and the barcode gets scanned. So what we have in the world is the naming of things via these digital transposition processes, where we have these alphanumeric names, if you like, for things, which in terms of instances are unique instances. That's one bag on one flight, once only. and concepts, which is this generic product, which is the sardine can there on the right, of which there are many instances. So we have these elaborate systems of naming through alphanumeric modes. So this is a form of using calculation to name, and have systems of number, which essentially name things in a world, and with much greater precision than is possible in natural language. There's more than one Bill Cope in the world, there's more than one Mary Kalantzis in the world, but by the time you reduce us to unique identifiers, which is our email address or our cell phone number, we are uniquely named as proper nouns in a way that where natural language is messy and not terribly, it's troublesome in a whole lot of ways. So that's the first thing we do in this space. We use alphanumeric systems which are reduced to binary numbers for the purposes of naming things in the world. The second thing we do is, having named the world, we calculate the world. So if we go back to this for a second, you know, there are a certain number of bags on the plane, they get weighed. So we check the weight's okay. When I get to the checkout, I've got 4 of these things, they get calculated. There are that many fewer on the shelf. So what we do is, having named the world in these very clear kinds of ways as instances and concepts, what we then do is we calculate the numbers of things, the number of instances that fit with a certain concept, for example. Now, this is actually one of the great geniuses of the computer age, who had Claude Shannon, a funny, eccentric kind of person, who rode unicycles, amongst other things, and juggled. And he came up with a fundamental insight, which was the on and off charge of an electrical current could be used in a system of binary notation or binary number to calculate the world, right? So his first insight was, you know, electrical currents are the way to go. And the second insight is that he discovered a 19th century philosopher named George Boole, and said that we could build elementary forms of what's now called Boolean logic using this on-off switch, this plus minus thing. Now, in fact, beneath calculability, it's not a digital world, it's a binary world. It won't work in base 10, it only works in base 2. So this is, you know, this is the elementary rudimentary form of all calculation. Now, what we can also do, as well as calculating the number of things, we can measure things across gradients. And what we have is, we have all these devices that measure ourselves. Even, you know, the opening of a door gets measured. So we live in a world of these ambient measurements, which are reducing calculations again to number, which the system keeps in this binary form. So when we walk around with our phones and we've got GPS calculating things about our position, it's in terms of all these reductions to number. Same with time. So these imminent things in the world which are measurable across gradients are also the third aspect of the transposability of meaning through calculation to meaning. So if the transposition is a meaning in the world in one form, you know, visual, textual, you know, an object or whatever, into number, and then back to some kind of object. But the back to part, that last part, involves rendering. So what we've had in the digital world, really over the last, you know, half a century, it's taken a while to evolve these systems, is systems for rendering, for example, written language. This is you know, the logic behind PostScript, which is that what we do is we create a representation of a character with a whole lot of pixels. This is what we do with image as well. It's still pixels, but in this case, it's color images, which are reduced to red, green, blue, RGB. Down the bottom right-hand corner is the LCD version of that. So what we've got going on our screens is this crazy, insane, you know, X million megapixels across 16 million colors. Who would make calculations like that? We would never do it. But the process of rendering, which is taking an image in the world, a text or something in the world, and turning it a number in order to reproduce it somewhere else, involves this intermediary stage of calculation. So to come back to our broad definitions and narrow definitions of AI, in the broad definition, this is a crazy amount of calculation which humans could never do before. And you know, and we have scanning of barcodes where objects speak their names and all sorts of things which, the calculations behind that are insane numbers of doing things with zeros and ones, which are impossible for humans to do because of the scale of it. So these are tools which enhance our human living in a whole lot of ways. But the artificial intelligence part of it is, if we synergistically involve humans in the labeling process, we can then have ways to read what an image is. So for example, if I upload an image to Facebook and it's a landscape, there's a sky and there are some trees, Facebook's going to say it's a landscape because we know that there's sky at the top of a picture and there's green at the bottom, and enough people have labeled these pictures to say that they're landscapes for the machine in its dumb kind of way to know that if blue's there and green's here in enough numbers, it's probably going to be a landscape. So in a way, all the stuff around face recognition, voice recognition, everything is based on huge amounts of human ascription of meaning to these binary calculations. And of course, in the rendering process, it's not just two-dimensional. So text and image are two-dimensional. Here we have 3D rendering as well. So just to summarize, what I've tried to do here is illustrate these two definitions of AI in process, the broad and the narrow. But then when we get to the narrow, the ways in which this labeling happens are these two processes of supervised machine learning. So what happened was, Facebook might say, we think this is a landscape because we've got all this other data, and you say it is. Well, these are all synergistic relationships via these two fundamental processes. So I'm going to hand back to Mary now, who's going to start talking about the educational implications of what we've just been saying.
Right. So we've been talking about the theory about artificial intelligence and our definitions, but how does it work and how do you apply it in learning? And is the medium the message? What mediums are we using and what messages are we delivering in ecologies of teaching and learning? And how are they related to pedagogy? What's the relationship between our pedagogy and the technologies that we use? They're the things that we're going to explore with you now. So we wonder, in the broad definition, of course, we would see learning. It's about seeing learning in a way that would not be possible for learners to see themselves, self-seeing, or teachers to be able to see the effectiveness of their teaching. How can artificial intelligence respond to the need for learners and teachers to be aware of what's happening in the processes of their engagement? So we're going to deal with the broad definition to begin with, and I'm going to share with you the example of what we've been doing. For some years now, we've been working with grants from NSF and Gates Foundation and other sources, so far about $10 million worth of research funds, to explore the potential of the digital for creating learning ecologies that meet our pedagogical values, right? And this, what I'm going to show you, just snippets of it, and not the whole thing, of course, is a program that we've called Common Ground Scholar, which is a space we've invented for students and teachers to work collaboratively on any subject that you might want to teach or engage with. So the first example I'm going to give you comes from a page that we call Community in Scholar, or a site that we call Community. And in this site, what happens here is that the teacher will make a post here. I'm sorry, there's a bit of a pun here about Shakespeare, but the teacher is posting in this first screenshot an activity into what's called the activity stream, and the students are required, as they would be in any classroom, to engage with that activity by speaking back to the teacher and by speaking to each other about the question or the topic that the teacher has posted in the activity stream. If we go then to the right part, the second screenshot that's there, and we dig down further into the posts of the students that have appeared in the activity stream, we have something like a blog here where the teacher has asked the students to examine certain language features in Shakespeare. And again, what follows, as you can see, the post there is from the teacher, and if you were to scroll further down, you would see a huge string of responses in great detail where everybody in the class is required to respond. It's not just the one person in a traditional classroom who might put their hand up and give the right answer to the teacher, but here what we expect in this particular platform is that all learners engage, and of course each one will bring their difference, their own interpretation to the conversation. So it's classically classroom discourse. This represents classroom discourse, but it's also fundamentally transformed pedagogy. And what also happens as these activities go, it is possible that all this activity is recorded by the machine and data mined. By comparison, what happens in a traditional classroom, face-to-face, person-to-person, orally, is ephemeral. And it is very difficult to go back and analyze systemically what was said, what was done, what worked, what didn't work, who responded, who didn't respond. But in this space that we have created, high levels of engagement and high levels of accountability about that engagement in the traces that the machine can document. Now we move to another one of the other elements that we've included in this form, and it works on collaborative knowledge making, it works on peer-to-peer, there's no bell curve of performance, everybody is expected to work and help each other, and two of many, but two main ways in which learners engage is that they produce their multimodal text in the creator space, and after they've completed their drafts, they share their drafts with each others and they peer review that work and they provide detailed annotations. And what you're seeing here is the rubric on the right, which provides the framework for making the peer review and the rubric for making the annotations. And as you can see in the right-hand side where the reviews, there's quite detailed responses that learners can make, that teachers can make. In fact, you can include anybody in this process. So what we're applying here is both the broad and the narrow definition of artificial intelligence. The broad definition, the machine is doing elaborate calculations which are not feasible for the teacher to do. So the machine can tell what kind of, how much feedback there is, what the text looks like, how many annotations were made, how the learner regarded those annotations. So there's a lot of data being collected. In the narrow definition, we have been working now with our research team on machine learning processes where the machine learns from these reviews and the ratings and the annotations in order to give subsequent student feedback based on the experience of previous students. So when the teacher teaches this same course again, the machine will have within the system ways of responding to the coded responses that learners are making to the activities that the teacher requires. Now here, what I'm showing you now is the analytics site of this Scholar work. So we have teachers posting, students posting, multimodal work creations, multimodal teaching, interactions between the students, all of it happening in a digital space and all of it leaving traces that can be coded. And we assess as you go. There's no assessment at the end. It's not you wait till the end of the class or the end of the lesson to get a mark, a grade. The machine is tracking everything you're doing and giving you feedback immediately. Every student gets one of these. We call it an aster plot, like the flower with all the different petals. And the teacher, of course, can see every student's aster plot and also what the class looks like. This is a class one here. And the aster plot can be designed for whatever goals you have. In our case, we have 3 goals. And 3, as you can see here, are equally important. And it really matters for us in the digital space that all 3 matter. So one quadrant we call knowledge, and it calculates the degree to which the work that the students have produced has aligned with the rubric and the expectations, and that is really important. But equally important in the digital space is the level of focus. How focused have the learners been in the activities? How engaged are they? How have they participated in all of the activities required of them? So the quadrant for focus is equal to the quadrant for knowledge. But for us, in terms of our values as pedagogues, it matters to us, the 3rd quadrant, which we call help. The degree to which learners help each other succeed, in the quality of the peer-to-peer feedback, the quality of the annotations, the degree in which they make knowledge together and they contribute to whatever the subject is in powerful ways as producers and not just as consumers. So the help component in any e-learning ecology matters significantly, and it's an affordance of the digital that we can exploit for our values and our purposes. So these 3 quadrants operate and collect data. On the right-hand side is a key about the kinds of elements. You can click into these petals, and every student, every learner, adult, child, college student can click in and know exactly what is expected of them. There are no hidden exam questions. There are no tricks. It's all very explicit. The rubric is there. The trace of everything you've done is there. The machine is collecting data. It's providing feedback to the learners and the students as they go, just in time and when it's required. This is what's possible with artificial intelligence, both in its broad sense and its narrow sense.
So I'm going to conclude now by moving on and talking a little bit about the narrow sense. But firstly, I want to talk about some aspect of the broad sense. Here we have in this aster plot a class that, in fact, this particular class was running for 8 weeks, and it had in fact, it was a course. It had 30 people in the course. And what's interesting is that we've collected more information about what's going on, including a lot of qualitative. They're not just quantitative things, they're qualitative human judgments that have been given quantitative proxies. So for example, with a rubric, what you do is you say, there's a rating of 1 to 4, let's say across 4 criteria. You describe those very, very well, but they're actually very complex human judgments that we have crowdsourced, if you like, across the group. And the crowdsourcing theory runs, that a number of participants who are peers are equivalent to experts if you kind of add them up and average them out. That's the kind of theory. So what this is this is not just number. This is complex human judgments that have been registered in number and that have with them justifications of why that number, they have qualitative justifications as to why that number's been ascribed. Now, what we had in this particular class, and this is the broad definition of AI, is that we had 14,500 pieces of actionable feedback. How could a teacher ever give 14,500 pieces of feedback? And who knows, in a regular class, there might be feedback going on, but it's not structured and it's, I asked the person beside me or something. And in fact, what there were this is based on 3.5 million data points, which is lots of classroom conversations, like the Shakespeare one that Mary showed you, several peer-reviewed projects, some surveys. And look, one of the points that we want to make is that the learning management systems we currently have in terms of AI are irretrievably unsalvageable around their underlying data structures, which is upload, download a file, look at a video. All that can be analyzed is the crudest of things. And what we've been working on in this particular environment is 20-something, 26 different data types and highly granular activity, which is one comment, one annotation, one coded annotation, one review. That's the 3.5 million pieces that happen there in many, many different kinds. And the trouble with most learning management systems, they're just really file upload, download systems. And what we've done here, which of course Facebook and Twitter have done as well, is we've abolished documents, we've abolished files. It's a huge database which in a very granular way keeps on rebuilding itself on the fly every time you access it. So there's a fundamental underlying architectural problem with most learning management systems, which means they'll never be able to do effective AI.
Can you say that once we ascribe the labels to the task, the machine then does the rest of the work?
Right, exactly. And part of it is, look, where does the labeling happen? The label happens with coded annotations. The labeling happens with rubrics. Yes. So in a sense, we enlist the teacher and or the course designer as people who do that labeling, right? And the broad AI definition is there's a hell of a lot of labeling going on here and a hell of a lot of calculation. Now, what I'm going to do now is talk to you a little bit about the narrow AI definition. So this is, so the narrow definition is learning from the learners, detecting and offering feedback on higher order thinking. This is a project that we've just been working on or just completed recently with the National Science Foundation, where we've got kind of inconclusively encouraging results. We're working on this. This is a work in progress. So what we've got here is a piece of work on the left. So Mary and I, with our masters and doctoral students, who are all teachers, we've now got a corpus of 30 million words and tens of thousands of annotations, and we've given them a coding frame where they code things as evidence or as critical thinking. We've got a coding frame with a dozen things where we're looking for high-level thinking. And what we're doing is a plus is a good example and a minus is a bad example. So we want them to be coding for things where you haven't succeeded to meet this thing, or you have. So we've got, in fact, if I think about it, 32 different codes going on. And what we want the machine to be able to do is see if the machine can detect higher order thinking in order to give students feedback on the fly around these higher order. Now, this is very ambitious, but it's us trying to think where, in terms of artificial intelligence in this narrow definition as machine learning, we might be able to achieve something. This is another project that we're working on right now, in fact. And I'm sorry that this is a little bit hard to see in these screenshots. You really kind of need a live demo version of it to see what it works. So there's a written text on the left, which might be another student's work or your own work or a text that you're reading, and you're highlighting bits and building a concept map around the node types. So you pull across the node selector, you highlight a bit, and you try and underline the thinking that's beneath your own text, someone else's text, or an assigned text. And what we're hoping to do is train the machine to understand the underlying thinking in texts in order to give students feedback. Again, this is phenomenally ambitious kind of project. Essentially what we've got is, this is a concept mapping tool where artificial intelligence is going to be bolted in down the back. So look, I'm just giving you a sense of
we're testing it first with in the medical area where the ontologies are more stable.
Right. So we first tested this with grade school students,
yes,
doing information writing.
Yes.
But what we decided to do now is to go to medical students where the labeling schemas,
yes,
otherwise known as medical ontologies, are very, very stabilized. In the United States, they're stabilized around insurance and billing, to be quite frank. But nevertheless, so we're hoping that in a domain where the labeling schemas are very, very stable, that we'll be able to really produce something which is very, very rich. And we're working now in medical education around that. So what we've done here is, in this talk, which we're now coming to an end, Mary and I have written up these ideas in these two books published by Cambridge University Press, published this year, to be quite frank, where we've tried to think in theoretical terms about this world of meaning in general and digital meaning in particular. And what these books do, in fact, is we've been talking about ontologies, which is labeling schemas. These are a kind of a meta-ontology of meaning for the digital world, a very ambitious project where we might sort of comes a bit unstuck and unravels a little bit around the edges because it's so ambitious, but where we think some of the insights that we've come up with may be hopefully of some use to some other people. If you'd like to join us in this social media world, go and sign up on the Scholar platform. Sign up is open, and a lot of what we showed you is open for general users to do. So Scholar is there, cgscholar.com. Go and sign up, create an account. In that, you might like to join our community, which is our kind of quasi-blog, but we do it in Scholar, which is called New Learning. So go and search for New Learning. There are our email addresses, and we also have a Twitter page, and we have a Facebook page as well.
And you might wonder why we have so much, but in the world today, when you're doing research, you want to be able to get the wisdom of the crowd. So we do encourage visiting scholars, we encourage collaborators. We teach and research what we're teaching, both in terms of its content, but importantly for the purposes of this conference, is how have we harnessed the affordances of the digital? How are we exploiting artificial intelligence for the positive, creative purposes that educators need to use it for? And how do we test it as we're doing? Because it's no good just simply downloading, as Bill said, the existing tools, because they were invented at a time when the whole idea of digital learning and artificial intelligence in education was marginal. It wasn't core business. Core business was the gold standard of face-to-face, in-person classroom, 1 teacher, 30 students, sometimes more. So it's not a finished journey, and this is really important for all of us to know, that we need to create the tools of our own workplaces, the tools for teaching and learning that we design and test in order to maximize the human part of the digital, how we use the digital for human purposes, not imagine that it's using us for some purposes beyond our control. So thank you for allowing us to share our work so far with all of you.
And let's hope we can meet in person sometime, who knows when, given the way the world is. Bye, folks.
Bye-bye.